Now, as far as a combinational circuit is considered, what are combinational circuit? Combinational circuit are those in which there is no storage of information. That means there is no memory. Okay, you can use a multiplexer to implement any combinational circuit, or in other words, any Boolean function which does not depend upon memory. Okay, so that is something that is very important. Any Boolean function Boolean function of a combinational circuit can be implemented, or you can just say any combinational circuit can be implemented using MUX alone. Okay, you don't need anything else. So if you have some particular functionality, just like a subtractor or adder or any combinational circuit you can think about, all of them you can implement using multiplexer. So let me show it. So let's take the full adder as an example. Full adder. The sum output. Okay, the sum output of a full adder. The sum output of a full adder. So first let us write the truth table. A full adder has three inputs: A, then you have B, and it also has a carry in. So these are the three inputs, and sum output is what we are considering. S is the sum output. It also has another output which also we can consider if required. That is C out. And sum. So input 3 bits can be in one of the 8 combination. So that is the first 4 combinations, and then you have 1 0 0, 1 0 1, 1 1 0, 1 1 1. Okay, so what will be the outputs? When you add these 3 zeros, you are going to get 0 0. Next one, you are going to get 0 1, again 0 1. Then you have 1 0 because you have 1 plus 1, and here again 0 1, then 1 0, 1 0, 1 1. Okay, so how to implement this using a multiplexer? So first you have to decide whether you are going to use an 8x1 multiplexer or a 4x1 multiplexer or even a 2x1 multiplexer. So if you are using an 8x1 multiplexer, let's say 8x1 multiplexer. So we are going to use an 8x1 multiplexer. So let me just draw the diagram of an 8x1 multiplexer. So it has got 8 input, 1, then 2, 3, 4, 5, 6, 7, so on more. Okay, so let me put it here. So these are the inputs, and it is an 8 by 1 MUX. So it has one output, 8 input. How many select line? I will have 3 select line, S0, S1, S0. Sorry, S1, S2, S3. Sorry, let me change this. S3, no, not S3, S2, S1, S0. These are the three inputs, and let's call this output Y. Now we want this Y to be equal to S. That's our aim. So then how can you? We know that the output going to depend on this select input and this data input. So data input, say D0, D1, D2, D3, D4, D5, D6, D7. So if I give 0, 0, 0 here, whatever I give here will come out. Now if I give this as A and this as B and this as C in. So that means I give A, B, C, all of them 0. Then what's going to happen is I should get a 0. Now if I should get a 0, then I should keep this as 0. So that way I have implemented the first row. Next, 0, 0, 1, 0, 0, 1, the second row. What should I get? I should get 1. And I know that output will be D1. So I am making the D1 equal to 1. Fixed voltage corresponding to logic level 1. So similarly, I can just go on. I can give the next one as 1. So just like I have written here the truth table, you just need to give those zeros and ones. Then 1, then 0, 0, then 1. That's it. So if you have an 8x1 multiplexer, you can implement the sum. S is actually a Boolean function of A, B and C n. Okay, A, B and C n. So that's it. So we have implemented the sum output. Now if you want to implement the carry output, that is another Boolean function, we need another 8x1 multiplexer. But now let's implement it by using not 8x1, a 4x1 multiplexer. You can do the same way by using 8x1. But suppose if the question is like I have a 4x1 multiplexer, then can I implement it? I want my Y to be equal to C out, which is a function of A, B and C. So this is 4 input and 2 select input, which are S1 and S0. So what should I give? So now you need to be slightly more clever, I would say. I can only give 2 of the inputs, either AB or AC or BC, okay, because there are only 2 select lines. So let me give the simplest way. I will give this as A and this as B. What do I mean by that? So when A equal to 0, B equal to 0, I have these first 2 cases. Next case is A is equal to 0, B equal to 1. Next case, A is 1, B is 0. The last case is, so I can distinguish between 4 different cases by giving these 2 inputs to the select line. So when A equal to 0, B equal to 0, I will have this D1 going to the output. This is D2. Sorry, let's call it as D0, D0, D1, D2, D3. So if A is 0, B is 0, D1 is what goes to the output. Now what should be D1? What should I give so that my output, if you look at the output is 0 irrespective of C. So if I give 0 here, that's it. So if I give 0, my job is done. When A equal to 0, B equal to 0, I will get 0. When C in is 0, I will get 0. C in is 1, also I get 0. So I get the correct output in that particular case. Now let's look at the second case. A is 0, B is 1. If A is 0, B is 1, what is that I am going to get at the output? I should get the output equal to 0 if C in is 0 and 1 if C in is 1. So how can I do that? Okay, so what I can do is I can make this input directly connected to C in, which is the third input. So if it is 0, 1 for A and B, I'll choose my D1, and D1 is C in. So if C in is 0, I will get 0. You see, C in is 0, I will get 0. C in is 1, I will get 1. So I am satisfying the C0 for A equal to 0 and B equal to 1 case also. Now let's look at the third case, that is 1, 0. So D2 will be chosen. And what should be D2? So that my output is 0 when C in is 0 and 1 when C in is 1. Again, it should be C in, nothing else. So that is going to satisfy this also. Okay, so now the last case, 1, 1. If you look at 1, 1, both are 1. So what should I give? This should be equal to 1. Simple, right? Very simple. So if I want to implement it by using a 4x1 multiplexer, where the Boolean function has 3 variables, then you need to group them like this, and then for each group you have a combination of select input, and then you have to decide what you should give here. Is that clear to everyone?
Yes, sir.
Okay, very good. So this way I can implement the S input also. So let me show that also. So S output using 4x1 multiplexer. 8x1 multiplexer is very simple. It is just direct implementation of. So here also I am going to give A and B. Okay, so this I am claiming it to be S. There are 4 inputs. Now quickly tell me, you tell me what should I give here. What should I give at the first line? Anyone? To get S output, I am looking now this particular column, A0, B0. What should I get? Anybody? Hello. What should I give at the first input if A is 0, B is 0? What should I give to the first input so that my truth table will be implemented? Students respond, otherwise it is very bad. If you have followed this, then you should be able to tell.
Sir,
Sir, Cin.
Cin, yes, very good. Cin. So if I give Cin, S will be equal to Cin, and you see that it is same as Cin, right? When it is 0, it is 0. When it is 1, it is 1. Now next one, 0, 1. A is 0, B is 1. What should I give? What should I give? What should I give?
Sir, C in complement.
Very good. C in complement. You see that? Everybody see that? If I give C in complement, that means when I have C in 0, I should get output 1. When C in is 1, output should be 0. Very good. Next one. What should I give? Next one. 1, 0.
C in complement.
C in complement. Very good. And the last case is
C in.
C in. That's it. So you can implement. So you need a C in bar here. So if you have a so one condition is that when you implement using multiplexer, you should have the inputs in direct form and complement form. Then you can implement using 4x1 multiplexer. Now let's try with 2x1 multiplexer. Okay, so that is even more interesting. Okay, same thing I would like to implement using 2x. So maybe I should write the truth table once again, or maybe I will copy it and put it. Same thing, same function. Let's go a little down so that it is. All right. So now I am ready. What we want is to implement it by using a 2x1. Let's take again S. So it has 2 input, 1 output, and 1 select line. Now there are 3 inputs, so you can give any one of them to go to the select line. So which one you want to give? A or B or C? Anything is okay. From this truth table, it may be more convenient to give A so that you can see, you can split it like this. So this is A0 and this is A1. Okay, so that advantage we have with respect to the truth table. So let us give A itself. Okay, so I want to say S at the output. I gave A here. So what should I give here? Anybody? So now you need to think about, you have to think like this. This group of 4. This is some function, right? Some Boolean function which depends upon 2 variables. What is that function? 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, 0. Which function is that? By looking at the case of 1, you can write that function. When b is 0, that is b bar c in, you have a 1, and then the other case of 1 is this. Okay, so there are two cases where it is 1. First case is when b is 0 and c in is 1. So b bar c in, that is the term, min term corresponding to that. And then the next case is b1 c in bar. So if I give this here, then my problem is solved. So if I give b bar c in plus b c in bar. So now tell me the second input. So first input I have written. Now tell me the second input. So second input, you can look for the truth table here. What should I give? Look for the cases where it becomes 1. That is b bar c in bar plus b c. So what I am doing is I am using a 2 by 1 MUX. Now I need to generate these functions. So I can use another two by 1 MUX here, and another one here that will generate for this. Okay, and this has one select input. Let me put it on the top and bottom. So what should be the select? So let me give b as the select input. When b is 0, what should come? C in should come. When b is 1, C in bar should come. Same thing I can do here. When b is 0, C in bar should come. And when b is 1, C in should come. Clear? Is it clear? You can think about it in a different way also. We are implementing a 4 by 1 multiplexer using 2 by 1 multiplexer, and then we are giving as before. If you look at it is exactly the same thing that we have done. So instead of AB, we are giving BA. So that's the only difference, and that's because in our earlier topic we have seen that we need to exchange the direction of A and B, select input. Everything otherwise remains the same. Okay, so now let's look at another example. Let's say a full subtractor. I think I did not teach you full subtractor, so let me first teach you full subtractor, and then let's implement it using multiplexer. Full subtractor. So if there is a full subtractor, there is also a half subtractor. So full subtractor has 3 input, half subtractor has 2 input. So first maybe it is good to look at the half subtractor and then full subtractor. So 2 inputs. So what are the 2 input? So let's say A, B. How many outputs? Okay, maybe it is a better idea to take it as X and Y, because X and y, because I want to reserve b for borrow. So just like half subtractor, we have sum and carry. A full subtractor will half subtractor will have difference and borrow. Difference and borrow. So borrow and difference. These are the output. So let me explain. The two bits which I give as input, I can the operation that I am trying to do is x minus y. This is simple binary subtraction. Okay, there is no 2's complement or anything like that here. Simple binary subtraction. So if you have two digits and that digit can be 0 and 0, so you are subtracting 0 from 0. So the difference is 0. You don't need any borrow, so that is 0. Now I can try subtracting 1 from 0. Then you will run into problem. You cannot subtract 1 from 0. So first of all you need to borrow. So you borrow, so therefore borrow is 1. So when you borrow, it becomes 1 0. 1 0 minus 1 is 1. 1 0 minus 1 is 1. Are you with me?
Yes, sir.
Okay. Next case is 1 0. This is a simple subtraction. 1 minus 0. 1 minus 0 is 1. Everybody knows that. And you don't need any borrow for that. The last case is 1 minus 1. You want to subtract 1 minus 1. You can do that without any borrow. And the answer is 0. Right? So these are the this is the truth table for half subtractor. Now for full subtractor, how does things change? So now let me write full subtractor truth table. So you have x, then y, and then you have a borrow in, and then you have borrow out and a difference. This earlier we have carry in and carry out, so here instead of that we have borrow in and more. So you have 8 different possibilities: 0 0 0, 0 0 1. Then these three are inputs. Okay, so these are input and these are output. 0 1 0, 0 1 1, 1 0 0, 1 0 1, 1 1 0, 1 1 1. Okay. Now what do we mean by full subtraction? Subtract with the borrow. Subtract with the borrow. That means first you subtract x minus y, will get some result. From that you subtract b in. So this is the operation that I am trying to do. So this borrow in is actually the borrow that we have supplied to the previous bit position. Okay, so we have to think about it in terms of a something like this: 1 0 0 1 minus 0 1 1 0. So here I am subtracting 1 minus 0, that is 1. Now here you see that I have to subtract 1 from so 1 minus 0, I did not take any borrow here. From here I did not take any borrow, so this b in was 0. I could subtract without any borrowing. Now for next subtraction from 0 minus 1, I cannot do without borrow, so let me make it more simple. Let me make it as 1 1. I don't want to mess it up too much. Okay, so I have to take a borrow. So from here I will take a borrow. So that borrow will make it 1 0, and that will make it 1 0, and 1 0 minus 1 is 1. 0 minus 1 is 1. Now I have given here one borrow already. One borrow has been gone there. Okay, and so just for clarity I will just omit this case so that you will not confuse with B in and B out. B in of one stage is B out of the other. So B in means I have supplied a borrow to the previous position, that is second position I have supplied. So now I have only 0 there, and therefore I need, and I can't subtract 0 minus 1 again, so I can't subtract, so I need to take one more borrow from the next position. So B0 is so our focus is on the third bit position. So here the result will be again 1. So this is what 11 minus sorry, this is 0. Okay, 1 0 minus 1 1. Okay, so this is basically 12 13 minus 6. 13 minus 6 is 7. So that's what we are doing. So we are focusing on this particular position. This is our focus. So we have to somewhere focus on one particular position. So there is a borrow that we supplied, and there is a borrow that we need to take to that position. So what borrow that we supplied is what B in. Okay, so that is gone away, and the borrow that we need to take, that is in order to perform the subtraction from the next higher position, is B naught. Is that clear? So it's a good example.
Yes, sir.
Yeah, okay. So now let's say if that is the case, now you can write all of this. So first I will do 0 minus 0, and then again, so doesn't make any difference, everything is 0 means I don't need to supply, I don't need to take any borrow. Okay, next one. I have supplied to the previous position. Okay, but there is nothing to supply actually, but I have supplied. You understand what I am saying? X did not have anything to supply, but still it supplied. So how did it supply? By borrowing it supplied. That's the only way you can supply. So I have to borrow, then this will become 1 0 and 1 0, then out of that I will supply 1, it will become 1, so the difference is now 1. Is that clear? Or you can think it simply 0 minus 0, so that is 0, and then again 0 minus 1 I have to do, I have to borrow, and after subtraction it is 1 0 minus 1, that is 1. Next case, 0 minus 1, again similar situation is happening. 0 minus 1 I can't do, so what I have to do, I have to borrow. So I borrow 1, so it becomes 1 0, and 1 0 minus 1 is 1, difference is 1. Next, I have nothing to supply, but still I have supplied, that means I have borrowed. So after borrowing it became 1 0. 1 0 minus 1, that is 1, and then 1 minus 1, that is 0. Clear? Is it clear?
Yes, sir.
Okay. 1 minus 0, that is 1. Again 1 minus 0, that is 1. I have not borrowed anything for doing that. 1 minus 0, 1. 1 minus 1, 0. I didn't borrow anything here also. 1 minus 1, 0. 1 minus 1, 0, and 0 minus 0 is 0. I didn't borrow anything here also. Now 1 minus 1, 0. 0 minus 1, I have to borrow. So 1 0 minus 1, after borrowing I will get it 1 0. 1 0 minus 1, that is 1. Okay. Now if you look at the D column, that is the difference, it is exactly same as the sum output. 0 1 1 0 1 0 0 1. Look here. 0 1 1 0 1 0 0 1. So the implementation of sum and difference for full subtractor and full adder, they are the same. So the D is same as the S of full adder. But B is different from carry. Okay, so let's write the expression for B0. So how to write the Boolean expression for B0? So first of all, let me do this also. For half subtractor, D of x comma y is what? So this is also same. This is also it's basically an XOR operation. I can write it as x bar y plus, this is one case, 0 1, and then 1 0. So that is x y bar. I can simply write it as x XOR y. Next one is B x comma y. What is it? It is only one case, that is one, that is x bar. That is first bit is lower than the second bit. So it's just like the comparator that we studied in the last day. That is less than, the less than condition only we need to borrow. Okay, so first bit, if it is lesser than the second bit, then x is lesser than y, that is the case, it is borrowing to. Now coming here, okay, so the difference, just like as I told you, it is same as the sum of a full adder. So I am just going to write it as directly as x XOR y XOR b. Okay, so that is a repetition, so that is why I am not writing it elaborately, finding it out. What about borrow output? So let's use truth table. So the Karnaugh map. So Karnaugh map should have 8 cells, and x, y, b, 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. Okay, so let's enter in this 0, 1, then 1, 1, then 0, 0 0 1. Okay, that's the order in which you have to enter. So whatever is here in this truth table, I have just entered. Okay, so you can go the first 4 0 1 1 0 0 0 0 1. Okay, now is the grouping. So if you group it, this is one group, this is second group, this is the third group. So you can now write B out, which is a function of x, y, and B in, as x bar. The first group, if you look at x is equal to 0 and B in. Okay, B in is 1. Next is x bar y plus the last one is y b in. So that is the expression. Now coming back to our implementation using say 2 variable came up. Okay, so 2 by 1 multiplexer, implement B0 using 2 by 1 multiplexer. So it's a question. The question is implement B0, which is a function of x, y, and b in, using only 2 by 1 MUX. Okay, so we have the function B0 is equal to x bar b in plus x bar y plus y b in. So this we have just found out. Okay, now what I'm going to do is I'm going to do some manipulation so that we can easily implement using a 2 by 1 multiplex. So the way I want to bring it is like x bar into something plus x into something. Then I can give x as a select input, and I know what function should be given at the input of the multiplexer. So in order to do this, x bar into something plus x into something, so what should be that something? So for that I should have with all the term either x or x bar. Okay, the last term out of the 3 term I don't have x or x bar, so I cannot write it like this. So first thing I should do is to bring x or x bar in that term. So that is, how do I bring it? X bar b in, there is an x bar here, so no issue, and x bar y, here also x bar is there, but the last term I can say I can multiply it with 1, and 1 is basically x plus x bar, so I can write it as x plus x bar into y. So this is basically 1. I'm just multiplying it with 1 and writing 1 as x plus x bar and then y b. This is a manipulation I am doing. Okay, so then what can I do? So let me just delete this and then continue with the algebra. So now I can expand and collect all the x bar term. This is b in plus y, then plus y b in. So that is the x bar term. If I collect, x bar is here, x bar is here, x bar is here, and then plus x dot, there is only one x term, that is y b in. So this is a very favorable, but I can still simplify this, y plus yb. So what is that? I can take y outside and then it will be 1 plus b in, and 1 plus b in is 1, so you can just basically neglect this term. Okay, it doesn't make any difference if you have it or not. So that is y plus y b in is y dot 1 plus b in, which is equal to y. Okay, y dot 1 which is equal to y. So that is what I am doing. So I can write further simplify it as y plus b in plus x into y b. Now what I want to do is now y plus b in, I want to bring it in terms of so x bar into this is y plus by in, I want to bring it in terms of y bar into something plus y into something. Okay, so how can I do that? I can write it, so here already y is there, but I can bring in y plus y bar here. Similar thing I want to do for the next term also. You can write so this is already one term is there, which is y, so I can say y bar dot 0 plus y into b. So that way I can do it. Okay, so let's do some more algebra. This is x bar into collect all the y bar term, so y bar dot b in plus y if I take common, it is just 1, right? Y plus y b in is what? Y plus y b in is basically y dot 1 plus b in, which is y. Just like the same thing. Okay, that is already here, so I don't need to repeat this again. It's exactly the same thing, so I have written it as y dot 1. Okay, so that is a good way of arranging terms. Same given Boolean expression we have arranged in this manner. So now it is good to go. Okay, instead of using the truth table, I am using the manipulation of Boolean expression. That's the only difference. Okay, so let me just draw it. So I have a multiplexer to which I give the select input as x. It is a 2x1 mux, and I have two inputs, and this is my b out. So what I am giving, I should give here the first input is corresponding to x equal to 0, which is the coefficient of x bar, that is y bar b in plus y, y bar b in plus y, and the second one is, this is 0, so I can just simply write it as y b. Then I have to generate this. For that I use another 2x1 mux, okay, to which I give y as the select input, and when I give y equal to 0, I should get 0. And which one I am doing? Sorry, I have to do this one. Okay, so let me correct it. So y equal to 0. So this is y equal to 0. I should get this one. Yeah. So y equal to 0. I should get b in. Y equal to 1. I should get 1. Similarly, the second one. So this is the lower case. X bar is equal to 0, whatever comes. Okay. Now, sorry, x equal to 0. So now here also I give y, but the top one should be 0 and the bottom one should be b. Okay, so that's it. So this is also a 2 by 1 mux. So this is an alternate way you can find out things. So I have given at least 3 methods to solve using 2 by 1 multiplexer. One is using this method, and then this method, and the last method is like first you implement a 4 by 1 multiplexer using 2 by 1 multiplexer and then give the input to the 4 by 1 multiplexer. That is the third method. So you can use any of this method. Okay, all right. So multiplexer are very useful things. You can implement any Boolean function using any combinational circuit using them. Okay, so what about is there any other thing like multiplexer which you can use to implement Boolean function? The answer is yes. Decoders can be used to implement any Boolean function. So let's see implementation of a full adder using decoders. So I'm not going into the internal details of decoder that we have already seen in the previous day. So I am taking a decoder which has 3 input. So here I am taking the input as A, B and C in. So this is 3 by 8 decoder, simple decoder, okay, not priority, sorry, that is encoder. So this is decoder, and I am taking active high output. Okay, active high output. So that is going to have 8 output, 3, 4, 5, 6, 7, 8. Now these outputs you can call them as minterms also. Okay, they are basically the minterms. So M0, M1, M2. I think I told you when I taught decoders. M5, M6, M7. So these are available at the output of. So what we need to do? I need to make a full adder. So if I want to make a full adder, I need a carry output and a sum output. So sum output has which all minterms? Sum output has this one, which is M1, M2, M4, M7. M1, M2, M4, M7. Or in other words, I can say S is equal to sigma M1, M2, M4, M7. Similarly, carry out I can write in terms of minterm. Let's see what are the carry output. It is last 3 and then 3 and the last 3. So that is M3, M5 is not there, M5, M6 and M7. Yeah, so these are the. So what you need, you just take a OR gate and connect it with the required input. For example, S, you need an OR gate for S and you need an OR gate for okay. So let's implement. So this is, suppose if this is C0 and this is S, then what you can do is M1 you take, M1, M2 you take, M2, M4 you take, M4, and M7 you take. So that is a sum output, very easy. So decoder, in addition to that, you just need OR gates, and the number of input will be same as the number of minterms. And the C0, M3 you take, M3, then M5, then M6, then M7. Okay, so we can also implement B0. So then so we can take this as either S or D. And what are the minterms which are present? I think the cases where X is less than Y. Just note down the minterms for B0. Okay, 1, 2, 3 and 7. 1, 2, 3 and 7. You can also write it as 1, 2, 3 and 7. It is not necessary to repeat M. That is understood by sigma notation that it is minterm. Okay, so this is the OR gate for B0. So 1, 2, 3 and 7. Okay, so we have a full adder and a half adder. Okay, so this is you can now modify it as full adder plus half adder, not half adder, full subtractor. Okay, full adder plus full subtractor. Okay, so if you take these two, that is full subtractor. The last two, this is full subtractor. And if I take these two, then it is full adder. Okay, so I'll stop here.